Hi everyone, my name is Daniel and I'm here to present our work on simulation of optical tactile sensors of complex morphology. So this work has been carried out by myself, Paulo Pauletti and Shan Lu. We are from the University of Liverpool and King's College London. So if you're not too familiar with the GelSight sensors, this is what a flat GelSight sensor looks like. So we have this soft membrane that deforms when some contact or some object is contact against the sensor. We have a camera that captures this view from the inside of the sensor, and we have illumination specially placed such that the observed gradients correlate with the orientation of the surface of the membrane. And so previously we have proposed simulation methods for these sensors, and others have followed up. But for the more recent curved sensors, such as our GelTip sensor and other ones that are coming as well, we have the illumination placed at the base of the sensor such that the light travels through the membrane, as we can see here in this picture, such that the light is sort of or we attempt to have the illumination tangent to the surface. And so for simulating these finger-shaped sensors, the main challenge is to model how the light travels sort of around the sensor. And so in this paper, we have addressed this issue, and we have considered 4 different approaches. So this first one, the linear, is sort of a baseline that ignores this light effect, and it's just as if the light traveled through the core of the sensor and creates this conical field. Then we've implemented this method based on the intersection of a plane against the mesh and generates this light field that goes sort of through the top of the sensor and comes down on the back. Then we used an existing method for computing geodesic paths, so shortest paths over meshes. And here the field is generates a bit more oblique paths that go through the side of the sensor. And so on the back also go a little bit to the top. And finally, we experiment with a transport method that is an existing method as well that addressed the problem based on the transport of a vector on the mesh. So here we transport the vector parallel to the main axis of the sensor. And so here we can see that the field on the sides is always sort of parallel. And you can see here highlighted the main features of these different light fields. And the main difference here is that the linear always hits the mesh in a non-tangent way, while the other 3 methods sort of travel tangentially to the surface. And you can see here that the difference being very well highlighted. So in the linear light field, we always have illumination, even in areas that there's no contacts, while in the other fields, or for the other fields, we only have illumination where the membrane is being deformed by a contact. And so to evaluate this simulation method, we've firstly collected a data set with a real GelTip using a 3D printer as a Cartesian actuator. And so here you can see some samples of this data set. We've done the same thing for simulation, whereas here we've stored the depth map, so which is the input of our algorithm, and then we generate for the different light fields the corresponding data sets. So here you can see samples using the plane field. So here you can see a comparison of samples from the data sets using the different light fields. So the main characteristic again is that with the linear light field, we have this very bright background. So one of the characteristics of our method is that we use a real sample from a real sensor to generate the background illumination that is not captured by the simulation model. And so when we overlap that with the linear light field, generates those very bright images. And finally, we wanted to demonstrate that this method can be used to aid the development of novel morphologies. And so here we just experiment with this highly irregular shape based on, say, a humanoid finger or something like that. And you can see here so we use the linear light field to generate the background illumination and the others for the contact areas.
I noticed that your data was sort of collected when you were touching like this. Did you ever try to make contact and then shear?
So here we haven't, so we mainly focused on the color and the illumination. We haven't focused too much on the membrane physical properties yet, so we have been doing that in other works. So for instance, one of the main aspect, or one of the aspect that we somewhat address is the deformation of the raw depth map. So we use the same strategy that we used in the flat GelSight sensor, but here it doesn't work as well. But we are using, or we are looking to approaches for doing like shear and all that kind of stuff. Yeah.
Great, thanks.
Hi, I wanted to ask if there are any sources of noise for the sensor, and have you modeled those noise sources into the simulator?
So in this work, in this paper, we haven't addressed yet noise, or we haven't considered noise yet. We've done that for the GelSight sensors. There's also the possibility of learning the simulation method from data itself. Yeah, we thought about adding noise, but we haven't added that in the paper, but it's an interesting idea as well. Yeah.